We are now going to think about quantitative reasoning and arithmetic, which is the third module of the unit that I'm creating for ICME Amor. You will recall, if you watched modules 1 and 2, that it was about street mathematics and informal mathematics. And in module 3, we're going to be thinking about school mathematics and how it involves different kinds of mathematical skills. And much of the work won't be my own research, but I will be reflecting on other people's research and concepts. The insights that we had from studying children doing their own informal mathematics led us to a very positive view of children and mathematics. We found that children enjoyed solving mathematics tasks with us and often left the room after doing quite a lot of work with a big smile on their faces. However, mathematics teaching and learning in school continued to be challenging, and we could not quite understand why these bright children who solved tasks with us outside of the classroom often said, I don't want to go back to class, it's mathematics teaching now. And all they had been doing with us was mathematical tasks. So I decided to focus a lot on the research that was being done about school mathematics. And there is a well-known example from a study that was done by teachers in Grenoble, which became known as the age of the captain. I want to give you an example of what they report in their study, but in this particular case, it's about the age of the shepherd. So the teacher says to the pupil, in a farm there are 125 sheep and 5 dogs. What is the age of the shepherd? And the pupil takes a little bit of time thinking about it, then says, this one is difficult. I didn't think that we could divide 125 by 5. And then the teacher asks, could you do an addition? And the student says, yes. What would the answer be? 130. Could you do a subtraction? Yes. I'd find 120. So what is the age of the shepherd? Why do you do a division? The student takes a long time thinking, according to the teacher, and then says, I don't know. And there is a silence. But then the student decides to explain, because 125 plus 5 equals 130. And this is a bit too much. And 125 minus 5 is 120. It's too much also. But 125 divided by 5 is 25. That works, but I don't know if it's right. Now, what I find amazing about this example is that it's quite clear that the student is thinking. When the student divides 125 by 5 to answer this problem, the student has dealt with other possibilities and decided that 125 divided by 5 is the only one that gives a reasonable answer. Now, in this case, in this example, the question is about the age of the shepherd, but the phenomenon is known as the age of the captain. There's an amazing similarity between the phenomenon, the age of the captain, and street mathematics. And that is that the same child is at the same time able and unable to reason mathematically. The child is obviously reasoning, trying to use different arithmetic operations to find a reasonable answer. But there is a big difference between street mathematics and this child in Grenoble. In the informal economy, people are reasoning about relations between quantities. But the child, as well as the teacher, are really talking about arithmetic operations. They are not talking about relations between quantities. It took me quite some time to come to what I thought was a reasonable understanding of the similarities and differences between street mathematics and the age of the captain. But it was by reading the work of Patrick Thompson that I realized how crucial the difference between reason about quantities and reasoning about numbers is for understanding both phenomena. Thompson defines quantitative reasoning as the ability to analyze a situation in terms of relations between quantities and to make inferences on the basis of these relations. And he's very strong about it. He says numbers and numeric relations are of secondary importance and they do not enter in the primary analysis of the situation. And he goes even further. He says quantities, when measured, have a numerical value, but we do not need to measure quantities to reason about them. So Thompson proposes a radical separation between quantitative reasoning and arithmetic. And similarly, thus the philosopher Goethe was a historian of science who worked in France, who defines arithmetic as the science of numbers, which analyzes the behavior of various numbers in 4 operations: addition, subtraction, multiplication, and division. So there's no reference to quantities here. Now, what is interesting, once we realize that quantitative reasoning and arithmetic are 2 very different things, is that we actually realize that quantitative reasoning does not translate into arithmetic operations and vice versa in the way a word might translate from one language to the other. You know, I might say in Portuguese computador and in English computer, and you can go from one language to the other preserving something important, but quantitative reasoning does not translate directly into arithmetic operations, nor vice versa. Now, once we realized that, Peter Bry and I decided to investigate the relative independence of quantitative reasoning and arithmetic using statistical techniques rather than case studies. And we ran large-scale studies in which we tested children's quantitative reasoning and arithmetic when they were about 8 years old, and then we looked at what predicted their mathematical achievement when they were 11 or 12 years old. And it was quite easy to see that the prediction that we achieved by looking at quantitative reasoning and arithmetic was independent. So using regression models, we showed that different parts of the variance in children's achievement in mathematics when they were aged 11 and 12 were explained by quantitative reasoning and arithmetic. Research needs to clarify is how we can put the 2 together. The use of mathematics to understand the world requires a coordination of quantitative reasoning and arithmetic. Now, as I mentioned in the beginning, this presentation involves thinking about lots of other people's work, and one of them is Levin Verschaffel. Verschaffel and his colleagues Eric de Court and Brian Greer carried out a very broad and systematic research program on problem solving in school. They found that the majority of children's errors in solving arithmetic problems, what is called word problems, was not from inappropriate calculations, but actually from an inappropriate conception of the quantitative relations in the problems. And after about 10 years of intensive research, they suggested that there is no simple solution for how to coordinate quantitative reasoning and arithmetic currently, but they concluded that what we need is a radical change in the way word problems are introduced and taught in school. And if we reflect back on the dialogue about the age of the shepherd, the teacher's questions were all about the arithmetic operations. The teacher was not inviting the child to think about which quantitative relations might help a child to go from number of sheep and number of dogs to the age of the captain, because the teacher already knew that there are no such quantitative operations. If we follow the suggestion by Verschaffel and his colleagues that we need a radical change in the way word problems are used in schools, we can think of using language in schools, which is what we do in word problems, to help children imagine situations that they can mathematize. But we also need to think about using these situations in order to help the children bridge what they can do with their schemas of actions with the mathematical tools and form more powerful reasoning systems. Now, I have used the expression reasoning systems a few times, so now I want to stop to think about what I mean by this expression. The expression is taken by the word by Luria, who talked about higher mental functions as being performed by functional systems. He contrasted higher mental functions with simpler functions in which there is a task, a process, and an aim, and all of these three things are fixed. But he referred to higher mental functions as being more flexible in terms of the way the tasks are performed. So the task is constant, the result is invariant, but the mechanisms by which the task is performed can vary. Let's take Luria's own example, remembering. Most people would think that memory is something that only happens in the brain, but in fact, memory, according to Luria, is a higher mental function that involves variable mechanisms. So if we want to remember something, for example, yesterday was Mother's Day, and wanted to remember to buy flowers for your mother, you might have gone out of the house saying to yourself several times, I need to buy flour, I need to buy flour, gone to the market, done your shopping, but forgot to buy flowers. So if you had just repeated to yourself, you were just using the mechanisms of your body, your language, to help you remember. And you might have remembered, or you might have forgotten to buy the flowers. Well, you might have written a shopping list and put flowers in the shopping list. And if you put flowers in the shopping list, you are using an external mechanism. The shopping list is external to your body, but it's still part of your memory. Or if you are one of these sophisticated people who use their phones as a memory, you might have set an alarm in your phone to remind you to buy flowers. So the task was to buy flowers. You could have 3 different mechanisms for remembering to buy flowers, and you could have accomplished them by any of these mechanisms. So that's a system for remembering. Now Luria elaborates this work on the basis of Vygotsky's ideas. And he says that the concept of functional systems used by Luria is based on Vygotsky's ideas. And I quote, "It is the principle of construction of functional systems of the human brain that Vygotsky called the principle of extracortical organization of complex mental functions, implying by this somewhat unusual term that all types of human conscious activity are always formed with the support of external auxiliary tools or aids." The importance of the concept of extracortical organization of reasoning systems can be understood by a very simple example. Imagine that what you wish to do is to compare 2 quantities, 2 piles of oranges sitting on plates. Well, this is a reasoning task when you want to compare 2 quantities. You could just look at the oranges, the 2 piles of oranges, and think, which one's got more of it? Or you could count the oranges in one of the plates. Or you could weigh the oranges. They are already on a plate, so you put, and they are on identical plates, so you put each plate on a scale, and the outcome is that you make a decision about which one has more. Now, the importance of an example simple like this is that it shows how incorporating an extracortical mechanism into the comparison influences the way you compare. Estimation is imprecise. When you look at a pile of oranges, you can't see all the oranges. There are some oranges under others. You can't see them. So the comparison is imprecise. You can move to counting, and counting is precise. So that's a good way of comparing. But actually, counting doesn't take into account the size of the oranges, and you might, for some reason, want to take that into account. So if you weigh the oranges in the basket or on the plate, you can have a precise comparison of the weight of the oranges, but you don't know the number of oranges. So the choice of which mechanism to use, counting or weighing, depends on the specific aims of your task. So if you're trying to think, how can you divide these oranges without having to cut them up, counting is probably a better option than weighing. But if you sell things on the whole in large quantities you don't want to count, you might prefer to work with the weight of the oranges. The example shows how by incorporating a mechanism, a mathematical mechanism, counting or weighing, you can make your comparison more powerful because it's more precise. But it also shows that the outcome of the comparison is structured by the means you chose to use in doing the comparison. So mathematical tools enable our reasoning systems, make them more precise and more powerful, but they also structure the reasoning. They influence the way in which we think. Now I want to go back to the example of multiplicative reasoning that we thought about in Module 2. We observed 2 films of children solving multiplicative reasoning problems. One would be solved by a multiplication and the other one would be solved by a division, but neither of the children knew how to multiply and divide. They used the schema of one-to-many correspondence. That was a good reasoning system, allowed them to attain a right answer, but there was not a very powerful way of reasoning. Each step in the reasoning had to be constructed by itself. So if you actually wanted to solve a problem where there were 100 houses and 3 dogs living in each house, this process of one-to-many correspondence reasoning would not be a very powerful one. So moving from a reasoning system to using a different mathematical tool could make the reasoning system more powerful. If students were able to think in terms of functions, they could realize that there is a relation between number of houses and number of dogs, and knowing something about functions would make the reasoning more powerful. Now, it turns out that this is a very difficult concept to teach. As we saw in Module 2, informal mathematical reasoning based on the schema of correspondences often operates by scalar transformations. And scalar transformations are not always easy, so people need to go to a more advanced concept and understand functional reasoning. Lynn Streffland from the Freudenthal Institute and his colleagues studied in many different experiments how to attempt to connect students' understanding of ratio at the level of correspondences with the concept of functions. They came out with a very creative idea, which is about the use of tables and specifically ratio tables. We have used Streffland's work to help us design teaching that supports children moving from scalar reasoning to functional reasoning. And I am displaying here some examples of what we have used in our studies. With younger children aged about 7 and 8, we use tables that incorporate figurative elements into the table. So you can see in this example, the problem would say each child is going to have 3 balloons. How many balloons do we need? And the table has the balloons and the children, and the correspondences will be here. And this kind of problem we present to children with some gaps. So sometimes the gap is in the correspondence between 1 and 3, like in this example, the simplest correspondence. But in other problems, we might give the children, for example, the information that every if we have 2 children, we need 6 balloons, and ask the children to try to fill out the correspondences. And in these examples, the children can use the ratio reasoning, but we also have the opportunity to ask the children to reflect about the functional reasoning. The drawing in the bottom illustrates, an example produced by a child when the problem involved a relation between the amount of water and the amount of fertilizer that you need to use when you are fertilizing the plants in the garden. What teachers can do if they build such tables with the children is to discuss the fact that the connection between the amount of water and the amount of fertilizer at each point in the ratio table is always the same. And you would be surprised to find out that many children who will tell you that, for example, for 1 measure of fertilizer, you need 3 measures of water, will not be able to tell you what number you would get if you divided the number of measures of water by the number of fertilizer at another point in the ratio table. So these discussions can be used to help children understand, students understand, that functions express the fixed ratio between 2 variables in a ratio table. It turns out that this is also not the most powerful kind of mathematical tool that you can have, because this is still, to some extent, relatively limited in abstraction and generalizability. Now, discussing the concept of functions using human-made, student-made ratio tables is a very powerful way of helping students construct the very idea of functional reasoning. But my good friends Celia Hoyles and Richard Norse and their research team have shown that we can bring external tools like spreadsheets and make them part of students' reasoning systems in a way that not only helps the students bring up the concept of functions into the course of their activities, but also empowers their reasoning in a completely novel way. When students look at data in a spreadsheet, and I'm sure you can imagine what a spreadsheet looks like, they can see the correspondence between the values. They can use their scalar reasoning, so they can continue to use the reasoning systems they already have constructed, but they can empower their reasoning systems by talking about each of the measures being representable as a variable and the functional value being represented by a constant. So spreadsheets can not only empower the reasoning because they can create more abstract and generalizable formula, but they can also be used in bridging the gap between informal reasoning that focuses on correspondences and scalar calculations, and functional reasoning, which is a more generalizable kind of reasoning. IT technology in mathematics, as Celia and Richard suggested, is not just a way of empowering students' reasoning, but also a bridging tool that can be used to help students develop the concept of functions and then become able to incorporate such powerful tools into their reasoning systems. If we stop and reflect a little bit about all the steps that I have just talked about in the context of quantitative reasoning, we can now try to put together an overview that helps us think how mathematics classrooms can be a place where children learn to explore quantitative intuitions and connect the quantitative intuitions that they develop from using action schemas to mathematical tools. This is once again the idea that Freudenthal had, that children can start by mathematizing situations, and as they mathematize in situations, they incorporate formal arithmetic and algebraic tools into their reasoning. Building the connections between quantitative reasoning and the formal mathematical tools requires careful design of teaching. As I argued before, there is no simple translation between quantitative reasoning and action schemas on one side and arithmetic on the other side. So bridging these two ways of thinking in the classroom requires careful planning. But the ultimate result would be very rewarding, and it would be that all learners could be empowered by using mathematical tools as part of their reasoning. Before we finish, it may be worth having a little bit of time to think about the educational implications. So mathematical models can be built by students as they mathematize situations in the classrooms. The concept of functions can be developed as they mathematize multiplicative reasoning situations in school. Freudenthal's hypothesis that teaching that builds on quantitative reasoning is more likely to succeed than teaching that starts from the mathematical model ready-made can help us go a long way in thinking about bridging quantitative reasoning and mathematical models. I think the evidence supporting Freudenthal's hypothesis is increasing and becoming stronger as further research into children's problem solving is carried out. I want to give you some references to the work that I have mentioned and try to encourage you to look at Module 4. Module 4 will be about the place of quantitative reasoning in education and the two meanings of number, which offer a way for thinking about alternative theories in psychology and some reflections on working with teachers. Thank you for watching Module 3, and you can now proceed to Module 4.